All right, last video for this section, I promise. If you've made it all the way through, whew, you've got to be tired of me. Hopefully by now you are getting this and it's getting to be pretty redundant. All right, so we have a bicycle on top of a hill with a radius curvature r with a constant speed v, constant speed. Draw the forces acting on the bike and the rider. Derive an equation for the normal force acting on the rider in terms of m, r, v, and g. Then state two things about the problem that could be changed so the rider loses contact with the hill and becomes a projectile. All right, so first things first, free body diagram. We'll bring it over here. We'll free the body. We'll do the easy one first. We have mg, and then we have some kind of normal force that we know is definitely smaller than the weight. All right, so there has to be a minimum of this normal force, right? So the minimum of the normal force without losing contact would just be where the normal force equals 0. If the normal force is less than 0, let's not put that equal. If normal force is less than 0, then there's no contact. Okay, so when it's at 0, that means it is exactly leveled out by this down here. So let's go ahead and derive an equation for the normal force where the normal force equals 0. So we'll do the stuff that makes it go minus the stuff that holds it back, because that's the next step. Stuff that makes it go, mg, minus the stuff that holds it back, fn, equals m times a. It's a circle, so it's going to be v squared over r, centripetal acceleration. We know not to use the omega squared times r version of this because it's asking for v. It says in terms of mrv. That's your big hint. Don't use the omega version. Okay, so our normal force is 0, so we can just kind of ignore that. So it becomes mg equals mv squared over r. We have m's on each side, so let's clean that up. G equals v squared over r. Derive an equation for the normal force. Oh, this is not an equation for the normal force, is it? Well, let's keep on going. Let's get our minimum speed that we can obtain to get over this hill. V equals the square root of g times r. Okay, good. That'll come in handy, I'm sure. Now let's go ahead and get this normal force. So I'm going to start with that mg minus fn. Forgot what the problem was asking. I'm sorry. It's like 10 o'clock at night, 10:30 at night or something. So fn is going to equal, I'm going to add fn to each side, and then I'm going to subtract all of this over there. Mg minus mv squared over r. And simplifying that, I get m times g minus v squared over r. There's our normal force. I'm going to walk you through that one more time, cleanly. So if you didn't get it, and you're like, what the heck did this guy just talk about? I don't even know. One last time. I'm deriving. Derive just means show the steps to get to an equation for Fn. That's going to help me remember what in the world I'm doing. So starting with my free body diagram, I'm going around a circle. So I know that my minimum normal force is going to be equal to 0. So I can set this whole equation equal to 0 if needed. So I'm going to get the net force. So my net force is the stuff that makes it go minus the stuff that holds it back equals mass times acceleration. Stuff that makes it go is mg minus my normal force equals mass times centripetal acceleration because there is a circle. I'm using v because v was one of the terms that I'm supposed to use. Next step, use a different color to make sure you know what in the world I'm doing. subtracting mv squared over r from each side. And I get mg minus mv squared over r equals fn. And then for my final step, I'm going to just pull out the common m's from each of these two terms. So I get fn equals m times g minus v squared over r. Step 1, step 2, step 3. That's deriving.